This is the Professor, CBMD PhD, and today's Monday, August 17th, 2026. It is 5:01 and 17 seconds, p.m. Eastern Standard Time, and today's research, optics and chips. So let's hop to it here. Caltech breakthrough brings fiber optic performance to silicone chips. Date August 17th, 2026. Source: California Institute of Technology. Caltech scientists have created ultra-low-loss optical pathways on silicone chips that approach the efficiency of fiber optics and dramatically outperform existing technology at visible wavelengths. The breakthrough could unlock more powerful lasers, miniature atomic sensors and clocks, quantum systems, and more energy-efficient data centers. Optical fiber already forms much of the hidden infrastructure behind modern communications. It allows information to travel over long distances at high speed because the glass inside the fiber is extremely pure and its surface is engineered to be exceptionally smooth. As a result, most of the light entering one end can reach the other without being absorbed, scattered, or otherwise lost. Researchers refer to this as ultra-low-loss performance. For years, we have been working to translate the spool-based fabrication of optical fiber onto silicone wafers, while trying to preserve the fiber's hallmark of ultra-low loss. We have developed a method to print optical circuits made from the same material as optical fiber directly onto the same 8 and 12-inch wafers used for computer chips. This shift toward fiber-like performance, especially in the visible bands, will enable new technologies that benefit from negligibly low circuit energy loss. The researchers create waveguides nanoscale on-chip pathways that channel light using germanosilicate, the same type of glass used in optical fiber. They adapt the material to a lithography-based manufacturing method suitable for making devices on wafers. Instead of running in a straight line, the waveguides are arranged in spirals. This allows light to travel at a much longer optical path while remaining inside a very small area. The idea resembles winding optical fiber around a spool, but nanofabrication makes it possible to fit the path into a far smaller footprint. Germanosilicate waveguides demonstrate extremely low loss and are also readily adaptable to efficiently transfer light between optical fibers and semiconductor lasers, which is of paramount importance in reducing the overall energy cost of server infrastructure. At near-infrared wavelengths, devices built with the new Caltech platform have already matched the performance of some of the best previous devices made from silicon nitride. Silicon nitride is widely used in optical technology because it can transmit data with relatively little signal loss. The advantage becomes much larger at visible wavelengths. The new germanosilicate platform substantially surpasses silicon nitride in this part of the spectrum. Due to the comparatively low melting temperature of the material, we can put our devices into a furnace to reflow the surface of our waveguides to get their smoothness down to the level of individual atoms, which largely suppresses the severe scattering loss that has limited conventional visible PICs. At visible wavelengths, our recent platform exceeds silicon nitride's record by a factor of 20, but we have more room to improve. Reducing loss can have a dramatic effect on the performance of optical devices. Lasers produced with the new platform, for example, show more than 100-fold improvement over previous designs in how long their light remains coherent. The expanded wavelength coverage our method offers will support many important atomic operations, making chip-scale atomic sensors, optical clocks, and ion trap systems possible. At first, the effort to measure losses over distances of meters or even kilometers might seem excessive for devices that fit on a small chip. The scientific investigators acknowledge that it might at first seem a little ridiculous, but the researchers are aiming for losses that can be described by percentages over kilometers. After all, our chips are only 2 centimeters across, but in reality, there are a lot of applications where this would be very powerful. One example is the ring resonator, a basic optical device used in both scientific research and data transmission. Light enters the device and is directed into a ring where it can continue circulating for an extended period. This repeated circulation strengthens the light at particular frequencies. Although the physical ring may measure only a few millimeters, the total effective distance traveled by the light depends on how little energy is lost from the waveguide each time it goes around. That is where low loss over meters, or ultimately kilometers, really matters. The longer light can circulate, the higher the performance of resulting devices can be. For lasers that rely on these resonators to increase coherence, the benefit grows rapidly. Every factor of 10 decreases in loss produces a factor of 100 improvement in coherence. The ability to create ultra-low loss waveguides across visible wavelengths could be useful for many different technologies. One of the reasons this is so compelling is that it has a Swiss Army knife quality. It can be applied in a wide range of settings. To demonstrate that versatility, the researchers describe several devices made with the new material. These include ring resonators, multiple types of lasers, and nonlinear resonators capable of generating a range of frequencies. The researchers also see the current results as an early stage rather than an endpoint. We haven't gone as far as we want to go, but we made significant progress over the last 5 years, and that is what we are reporting on here. And this video was created for educational purposes only. My code name is Will, and Professor Christopher Brunet, leader of research scientist, ufologist, psychic computer technician, computer programmer, philanthropist, writer, mathematician, artist, photographer, film producer, chef, animal, and nature lover. My passion is world peace. Have a great day.